Hello everyone, today we're given a grid that's filled with empty spots or obstacles. A 0 represents an empty spot and a 1 represents an obstacle. We start in the top left corner and we need to find the length of the shortest path to reach the bottom right corner. We're allowed to move up, down, left, or right, but not diagonally. We're also given a number k, which is the number of obstacles we can remove along a path. If a path doesn't exist, we return -1, otherwise we return the length of the shortest path. Let's look at a few examples to get a better idea of the problem. Let's say we're given this grid and k is 0, which means that on our path we're not allowed to eliminate a single obstacle. Then the only valid path is the green one. This takes 10 steps, which would be the answer we would return. But what if k is now 1? This means that this new path is going to be our shortest path because we're able to remove a single obstacle to form this path in 6 steps. You should note that there is an alternative shortest path as well, which also only takes 6 steps, but since we're only interested in returning the length rather than the path itself, it really doesn't matter which one we look at. So now that we understand the problem a bit better, let's try and build up a solution. When I first saw this problem, I thought it was pretty complex. So I think a good strategy when you're solving harder problems is to first reduce your problem into something simpler. Let's go back to our original problem statement. To me, the part that makes this problem hard is the k value, and the fact that you're able to remove obstacles. Let's remove this part of the problem, so our simplified problem reads as, we have a grid filled with empty slots and obstacles. Our goal is to find the shortest path from the top left to the bottom right, avoiding all obstacles. So essentially, our problem is made easier by the fact that we're no longer given a k number and we can't remove obstacles. At this point, this problem should be pretty familiar. The keyword shortest path should tip you off to 2 graph algorithms. For unweighted graphs, we use BFS to find shortest paths, and for weighted graphs, we use Dijkstra's algorithm. If you don't know what BFS or Dijkstra's algorithm are, or what they're used for, then you might want to review your graph algorithms. I'll make a small digression here and say situations like this are what's really helpful for isolating what you need more studying in. If you aren't able to solve this problem because you didn't make the connection to BFS and Dijkstra's, or you don't know these algorithms at all, then your problem isn't interview questions themselves. Your problem is that you aren't necessarily familiar enough with the graph algorithms, and you probably need a review of them. If you're able to make the connection but failed to apply it correctly, then your problem is interview questions, and you just need a little bit more practice with graph algorithms. If your situation is the latter case, don't worry, that's exactly what we hope to accomplish in this video. Anyway, back to what I was saying. The word shortest path should tip you off to the unweighted and weighted shortest path algorithms of BFS and Dijkstra's. In this case, we don't have weights because each step counts as 1 unit of distance, so we're going to forget about Dijkstra's and use BFS instead. The code to solve the simplified version of our problem is pretty much a copy-paste of the standard BFS algorithm. To start off, I've made n and m to represent the max rows and columns. This is just for our convenience. We also have a queue called queue. I used Python's deck here, but that's because the syntax of a queue in Python is a bit weird, but for all intents and purposes, our deck here is really just going to be a queue. We start off the BFS by manually inserting the top left element. There are 3 values in our tuple, the row and column position of the coordinate, followed by the current distance. For the top left corner, the row and column are 0, 0, and the initial distance is 0 as well. Next, we have the start of our BFS, which is a while loop which runs while there are some elements in the queue. In our BFS, we remove an element from the top of our queue. If that element is the bottom right corner, we return the distance immediately. Remember that in BFS, we're expanding one level at a time away from our source location. This guarantees that the first instance at which we arrive at our destination, that will be at least one of the possible shortest paths. This is why we can be greedy in how quickly we return the distance. If we encounter a 1, which is an obstacle, we ignore the element and move on to the next iteration, effectively clipping this path. Remember that right now, in the simplified version of our problem, we're not worrying about removing obstacles just yet. We're thinking of them as unremovable. Finally, in the last part of our algorithm, we loop through each of the 4 directions, which I've initialized at the top. This is the movement of up, down, left, and right, and for each of these directions, we can now think of us taking a step from the current position to the new one. If this step is inbounds, we add it to our queue. We also need to use a visited set to keep track of the elements we visited and only visit unvisited elements. This also prevents us from going into an endless loop in our BFS algorithm. This is the entirety of our algorithm, and it should make sense to you how this straightforward application of BFS solves our simplified problem. Of course, this wasn't our original problem, so now let's bring back the obstacle removing part of the problem and see how we can adapt this simplified solution to our original problem. We need to handle two key things. The first is we need to keep track of how many obstacles we have removed on each path. So in this example, let's say k is equal to 1. We start in the top left and take a step down. We immediately have to remove an obstacle. So we need to somehow keep track of the fact that for this particular path, we can't remove any more obstacles. We can do this in our code by storing an extra piece of information in our queue. Along with the row, column, and distance of the path, we can store how many more obstacles we can remove from this particular path. I'll call this value lives, kind of like the lives left in a video game. Here are the changes we need to make to our algorithm to do this. Let me walk through these one at a time. It should make sense that for our initial value of the queue, our live starts out as k. We also need to edit the if statement where the grid is an obstacle. In our simplified algorithm, we could just forget about the path if we ran into an obstacle. But now we need to remove it. So we replace the continue statement with a statement which decrements the lives by 1, symbolizing the fact that we have used one of our k obstacle removals for this particular path. Finally, when we pop off the top of the queue and add new elements to the queue, we need to account for the current lives piece of information. Again, here are all the changes. Note that at this point, our algorithm still doesn't work yet. That's because we haven't handled our second problem, which is the fact that we need to have a mechanism for updating the lives and retrying a path if it has more lives. So let's say, for example, this is our grid and k is 1. Notice that if we take this path here, we won't be able to make it because this requires us to remove 2 obstacles. However, we take this path here, notice that we only need to remove 1 obstacle. Our problem is that for both of these paths, the 0 which I've highlighted green are the same distance away from the starting point. So there's no guarantee that our better path will get there first. So we might run into an issue where our algorithm mistakenly thinks that there isn't a possible solution just because the BFS happens to prioritize the bad path over the good path. How are we going to solve this? Well, our solution is to create a lives matrix, which is the same dimension as the grid. This matrix is going to represent the largest amount of lives that a particular position which has been visited has. This is a bit confusing, so let's walk through a scenario with these two paths. We start off in the top left with 1 life because k is 1. If k was 5, we'd start off with 5 lives. Now for the first step, with our green path, we don't use a life because it's not an obstacle, so our lives remain the same. However, in the first step of our orange path, we immediately lose a life because we need to move that obstacle. On the second step of our orange path, we don't lose a life because it's an empty space. But you should note that we can't afford to lose any more lives in our orange path because we've already used up our one and only life. But let's say if k was larger, say 5, then we would be able to lose 4 more lives. For the second step in our green path, we don't lose a life, so it stays at 1. I should point out that our algorithm does explore different paths. For example, it goes down here as well, but I just want to trace these two paths, the orange and the green one, just to keep things simple, because I'm too lazy to cover all the possible paths in this grid. Anyway, for the third step, in both the orange and the green paths, we don't lose a life, so the orange path stays at 0 and the green path stays at 1. Now for the fourth step in the orange path, we don't lose a life, so it stays at 0. But notice that from above, the fourth step of the green path also doesn't lose a life. So we need to update this slot to be the greater of the 2 lives, because otherwise we would get the wrong answer. Let's actually look into that. Let's not update this slot so I can just demonstrate what I'm trying to say. If we don't update the live slot to the better value, then we continue downward and we need to remove an obstacle. But we don't have any more lives to do so, so we stop the path. This obviously shouldn't happen because if we took the green path, we would be able to clear this obstacle. This is why if we encounter a live slot with a lower value and our current path has a higher value, we need to update it. In this particular case, the live slot has a 0, but our green path has 1 life, so we update the slot to the better of the 2, which is 1. At this point we continue downwards and we will be able to clear the obstacle below, which bumps our lives down to 0. And finally, we reach the bottom right corner by traveling downwards and our lives stays at 0. So now you've seen this example, how do we edit our code to implement this mechanism? Well, first we need to initialize our lives matrix, which is the same dimensions as the grid, and initially we can just put in -1s. And we're actually going to get rid of our visited set. The reason for this is we can actually visit the same slot multiple times as long as we're bringing more lives to that slot. As we saw with this slot here, we visited it twice because we were updating it with more lives, 1 life instead of 0. After we get rid of the code for this visited set, we're going to replace it by instead keeping track of lives. We only add new elements to the queue if they beat the existing amount of lives in the lives matrix. We also need to update the live slot for that position if we are re-adding it to the queue. And that's it, that's the final algorithm. Let's go over the time and space for this solution. For time, we have O of n times m times k. The n by m is the BFS time complexity, but for the k, well, this is the fact that in our BFS, we can revisit the same element k amount of times. Think back to this slot here, which we revisited. Remember that we only revisit positions if we can update the life to a better one. Well, for a given slot, worst case is that we improve the lives by only 1 each time. This would mean we could improve a slot k times, which means that we could visit a slot worst case k times as well. So, since for each one of the n by m positions we can visit it k times, our time complexity is n by m by k. For space, well, we're using extra space in 2 major spots, the lives matrix and the queue which supports the BFS. The lives matrix is O of n by m, however the queue can grow to O of n by m by k, so our space complexity is O of n by m by k. I think this is actually the optimal time and space for this problem, so we're at the end of this video. This problem was quite challenging for me when I first solved it, and I certainly had a lot of questions. If after watching this video you're still a bit confused, feel free to leave a comment and I'll do my best to get back to you. I do hope that this video in some way at least helped your understanding though. If you did find it useful, please consider liking and sharing the video and subscribing to the channel. As always, thank you very much for watching and good luck on all your interviews.